Hi, so today we're going to look at FPGAs or field programmable gate arrays. So these are neat little devices that you can use to implement any kind of logical circuit natively onto the chip itself. So you don't have any overhead, processing overhead for example, in microcontrollers or anything like that. And the reason we're looking at this today is I have a whole bunch of nice little projects planned for FPGAs that I'd like to demo on this channel at some stage. But first, let's see if we can at least get a Logisim evolution circuit running on an actual FPGA. So the board that I currently have is this Core 3S500E. It's a pretty neat board. So it has this nice Xilinx FPGA chip on here with 500K logic elements. And these are basically used to implement your logical functions. I would actually recommend you watch Dave Jones' video on what an FPGA is and how it works before jumping onto this one, because this may seem a bit confusing if you've never heard about the concept of an FPGA before. But in essence, it's basically a board that it's basically a chip that allows you to implement any kind of logical circuit natively. So it basically runs your logical circuits in real time. There's no processing overhead. It doesn't have any kind of microcontroller or processor on there. It basically just has a whole bunch of arrays of logic elements, or they're basically just lookup tables that are configurable to implement whatever logic function you need implemented. And you can configure them in real time and have your circuit running on this thing in real time. It's a very interesting concept. So the basic layout of an FPGA board is this is basically a very standard layout for basically any typical FPGA board. You have your FPGA chip on here. You usually have a few LEDs. In this case, I have 4 LEDs on this one. They are nice to have just so that you can at least see if your circuit is actually working. And then they usually have an crystal oscillator on here. This one is 50 megahertz. That's also a really typical value for any kind of entry-level FPGA board. And then you always have your three voltage regulators on there for the 3 different core voltages that are required by the chip. So yeah, it's quite interesting. If you're basically just getting started with electronics, then FPGAs would probably not be what you're looking for. I would recommend playing out with microcontrollers first. You'll probably be able to get away with most things by just using a normal microcontroller. They are much cheaper and much more durable, I would say. They don't actually, you don't break them as easily. But there's a lot of things you can do with FPGAs which you can't do with microcontrollers. So yeah, let's see if we can get something done on it. So you'll see I have this, I currently have this demo program, which basically comes with this FPGA. So they actually have a nice few demo projects for you to tinker around with to get started. And currently, you will also see that everything here is written in a language called VHDL. So it's basically a hardware description language. It's basically how you describe logical circuits in a language, essentially. It's quite neat. So right here I have a demo basically running an LED sort of counter, I suppose this is. So this basically just counts up using LEDs, and this is basically what it looks like running on the chip itself. So currently the configuration that I have here is I have my JTAG programmer from Xilinx plugged into the JTAG header of the board, and then I'm currently powering this board up using this USB to TTL converter thingy. I'm just using this for power, so this is just to get the 5 volts and ground onto the chip itself. Now I'm using a little bit of a this may seem a little bit weird. So actually, this board actually comes with 2 0.0 millimeter pin headers instead of the standard 2.54 millimeter pin headers. So it's not a very standard pin header that you have here. So it's a little bit hard to get things connected to this board. You actually need the correct expansions and the bright size jumpers, which I don't have, unfortunately. I've ordered a whole bunch of things for this board, but I'm still waiting for it to arrive. So you can see currently we have this demo program running on here, just basically counting up the LEDs. So the way this basically works is it uses the clock signal from the 50 megahertz clock, and it basically just uses counters and uses the output of those counters to essentially turn the LEDs on and off through probably like a multiplex or something. Let's see if we can go ahead, jump into the software and see if we can play around with this thing for a bit. So I'm going to open up the sample program that we have here again, and I'm actually going to close this thing and let's see if we can create our own program. So I'm going to create a new project. I'm just going to call this let's create an AND gate, because why not, just to show the FPGA software out a bit. So I'm going to just make sure that the family here is correct. It's a Spartan 3E chip that I have, and then the device is the XC3S500E. And it's in the PQ208 package, which is all correct. So I'm just going to hit next and finish. And then we have a new project for our FPGA. And I'm going to add a new source to this. So you actually have a whole bunch of choices here. You can use Verilog or VHDL, or even you can even draw your own schematic if you want. It's quite neat. So VHDL is like the standard language, the one that I'm most familiar with. It's a very kind of verbose language, at least compared to Verilog from what I've seen. Verilog is a little bit, I would say, easier, and you can get more done with it a little bit quicker. But I happen to be more familiar with VHDL. VHDL is a little bit more strongly typed, I would say, and also it's less error prone. You're more likely to have a working solution in VHDL than Verilog. With Verilog, there might be unforeseen errors that you can run into. It doesn't really warn you when things goes wrong. With VHDL, you kind of get warnings about pretty much everything that seems off to the synthesizer. So let's actually go ahead and create a schematic, because you can actually do that. So I'm just gonna say, let's make an AND gate, and gate, just like that. All right, then in the schematic pane, we can just go ahead and hook up a gate to this thing. So I'm gonna go to symbols. I'm just gonna search for AND2. So we want a 2-input AND gate. Yeah, that's quite neat. And then I want to hook this up to I/O. So I'm just gonna put some input and output pins on this thing. And then we're gonna look at how it actually gets synthesized, because it actually gets converted to VHDL, and then that VHDL gets synthesized to the board. It's quite interesting, actually. So let's look at the design here. Design utilities. Let's see if we can synthesize this thing. Yes, we want to save. Now, one thing we can do is we can actually view the RTL schematic, which is kind of neat. So this is a schematic of how it's actually going to be implemented onto the FPGA chip itself. And here you can see this is just up to inputs, our AND gate, and then the output. Quite neat. And then we can also view the technology schematic. So this is actually quite interesting. So this actually shows you how it's going to be implemented on the FPGA chip itself. So we have like our inputs, some kind of input buffers, it would seem, and then the actual AND gate itself. It's actually quite interesting that the AND gate shows up here as a dedicated AND gate instead of a lookup table, which implements the function of an AND gate. But as you build more sophisticated circuits, you will see more lookup table stuff. So it probably has a whole bunch of built-in AND gates, probably to make things a bit more efficient in certain designs. It's quite interesting. But we can also go ahead and simulate this. So let me show you how we can simulate this thing. We need to head over to simulation. I'm going to right click, add new source. I'm going to create a VHDL test bench. So this is normally what you use to test your circuits out. And test. Let's do that. Yeah. Finish. And here you can see our test bench that was generated. Well, this is just an empty test bench. It's not going to do anything. So let's write some test logic for this thing. So we want to say, let's wait for 10 nanoseconds just to start out. And then I'm just going to set the inputs high and low. So I'm just gonna set this guy. So the first input, when the first input is low and the second input is low, we of course expect the output to be low as well. I'm just gonna add this in here. And then we basically want to test for each case of an AND gate. So there should be 4. So you have low, 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 high, high, low, and then finally we have high and high for both inputs. Oh, this is not gonna. There we go. So we can actually run a simulation with this to see how it works. Simulation, Isim simulator. Let's first check the syntax. And then let's go ahead and simulate this thing. There you go. So now it's going to open up in the simulator. I'm just going to change the period here to something like 100 nanoseconds. There we go. I'm also going to zoom out a bit. There we go. This is it. So here in the simulator, you can see that when both signals are low, the output is low. When one is low and the other one is high, the output is also low. And when the one is high and the other one is low, when both are high, then the output is high. So yeah, low, high, 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 low, high, low, low, high, low, high, high, high. Yeah, so here we can see the simulation of the circuit. Very neat, very neat. So let's go ahead and jump into Logisim and actually simulate this thing. Let's exit the simulator. Exit, yes, I want to exit, close project. Let's create a new project. I'm just going to call this tutorial. Next. Yeah, we're fine. Finish. Perfect. So now that we have it saved, let's hop into Logisim Evolution and create an actual circuit for this thing. All right, so we're in Logisim Evolution. So what we want to do here is I want to create a simple little circuit that we can run on the FPGA. So I'm going to use a similar example to what the actual board comes with. So we're also going to run the LED. Yeah, so I'm going to create a simple little LED circuit that will basically strobe the LEDs, but instead of doing it based on the clock, we're going to do it using the reset button. So every time you press the reset button, it's going to light up the next LED. So let's go ahead and do that. Gates IO. Yeah, we want LED. South, yeah, so we have 4 LEDs that we can play with. Perfect. Now we have a reset button. Let's take a button. Right, this is our 4 LEDs. This is our reset button. Let's do something with them, right? So I'm going to create another sub-circuit here called just LEDs. And then we're going to need to hook up some IO to this thing. So I'm going to create a reset button input, and then we need some outputs as well. So output yes, facing south. There we go. We have 4 of these. So we're going to need a counter for this. Let's Arithmetic, nope. Let's see, memory counter, yeah. I don't like this appearance. I'm going to use a standard classic Logisim appearance. It's much nicer. So now let's see what all these pins do. There's a lot of pins on this thing. Up when 1 counter increments, when 0 counter decrements. So we obviously want this to be 1 because we want it to increment. So I'm going to hit power up to this thing. There we go. Let's see, this is load. When 1 loads data from input. We don't want to do that. Enable when 1 counter increments or decrements. Yeah, we do want to do that. So I'm going to hook that up to power as well. And then this is probably just a clear. Yeah. So we're going to hook these two up to ground. I'm just going to put ground on there. There we go. And then the clock is going to be the reset button. There we go. And this thing is going to be a 2-bit counter because we want to count up from 0 to 3. Because we have 4 LEDs here. And then we need some kind of a demultiplexer. So let's see, plexers, demultiplexer. There we go. Select bits 2. Yeah, seems fine. Let's hook them up. There we go, and the counter output can just be the select of the demultiplexer, and then this input right here is just going to be hooked up to power. There we go. That should give us the functionality we need. So there we go. We turn on the next LED every time we count up. All right, it functions as intended. One more thing I want to do here is I just want to also include the enable bit on the demultiplexer. The reason why I want to do this is because there seems to be a bug in Logisim Evolution where if you don't include the enable bit on the demultiplexer, it will actually still export the VHDL for your multiplexer with the enable bit included. And when that happens, the enable bit is basically going to be disconnected. And that's going to cause errors when you synthesize the VHDL in your FPGA software. And we don't want that. So to avoid this, we just enable the enable pin on the demultiplexer and to get up to power. And that will solve that problem, hopefully. We'll see. Now I'm going to go back to the main circuit. I'm just going to put this thing in here. Using the classic Logisim appearance, of course. So let's hook these things up, shall we? And now I'm going to hook up the reset button. There we go. Perfect. That's quite strange. Yeah. So every time we press it, it works as intended. Perfect. Now one final thing I want to do here is take into consideration that the LEDs on my FPGA board are actually active low instead of active high. So Logisim Evolution always assumes active high on basically everything. So you need to just take that into consideration as well. So I'm going to change these LEDs to be active low. So I'm going to set active on high to no. So now it's going to behave basically the opposite of what we want. So I'm going to need to include NOT gates on these LED lines. So let's go to gates, find our NOT gate. Okay, there we go. We want to face north. I don't want a narrow symbol for it. There we go. Perfect. That's it. So now it's functioning as intended again. So let's go ahead and export this thing. So I'm just going to head over to FPGA, hit synthesize and download. We first need to annotate because in VHDL everything needs to be labeled, of course. And then we need to hit execute. Now I'm not going to worry about the board that's selected in the settings. It doesn't actually matter. We don't care about that. I just want the VHDL code that implements the functionality. So I'm not actually going to map any of these I/O to any board because we don't care about that. Now it's going to warn me that some I/Os are not mapped. I don't care, so I'm just going to hit yes. And it created the VHDL files that we need, which basically describes the circuit. So let's go ahead and look at what that looks like. So here in VHDL, yeah, it should be under untitled or maybe even untitled 2. I'm not actually sure. VHDL circuit. Yeah, this looks like it. So what I'm going to do is I'm going to copy these 3 folders here. I'm going to ignore the top level because the top level, I don't really understand what this top level is all about. It's a top level that doesn't really make sense. Maybe it's for mapping to when you map IO to specific boards or something, but I'm just going to ignore that. That's just going to make things more confusing because we already have the main in here, and the main is kind of top level enough. We don't really need a higher level top level than that. So I'm just going to copy these 3 folders over to the project. Let's see, Xilinx project, VHDL. I'm going to go to our tutorial project that we created. Just going to create a source folder in here, SRC, and paste these files in there. Now I'm going to head over to the FPGA software and we're going to basically import the VHDL that we've exported from Logisim Evolution. And then we're actually going to run it onto the FPGA board and see it in action. So I'm just going to add source, go to source circuit, basically just add all these sources in. There we go, add source memory, there we go. So let's just add these guys. Perfect. So now that all the sources are added, we could see the VHDL code that basically describes the circuit that we created in Logisim Evolution. And this is it. So you'll see that we have our counter here, and then also our multiplexer here, or demultiplexer. Perfect. So let's go ahead and synthesize this, shall we? Perfect. So now we can actually look at what this what the RTL schematic of this actually looks like. So we can say we have our main component here. If I open this, we have our LEDs subcomponent. And inside of that, we have our counter and our demultiplexer. We can expand the counter, and here you can see the logic that implements the counter functionality. So we have an adder here, something else like a flip-flop or something, a D flip-flop. And then 2 AND gates there. And for the demultiplexer, we just have a bunch of AND gates with some negated inputs there. Very neat, very neat. And then we can also see how it's actually going to be implemented on the FPGA chip itself. So if I go ahead and view technology schematic, so this is quite interesting. So this is what the actual implementation is going to look like on the FPGA. So it's going to actually implement this functionality using lookup tables. So here we can see we have our input buffers, and then we have the actual lookup tables. So here you can see the schematic that is being implemented by this lookup table. And here you can see the values that are actually in the lookup table. So this looks like a 4 input lookup table, or two input actually. Yeah, so here you can see the 2 inputs for the lookup tables and the output that it will produce. And that's basically how it implements logic using lookup tables. So it's basically just a whole bunch of lookup tables implementing the logic that we need. Quite neat. So let's actually go ahead and run this on the FPGA. But before we do that, we first need to map the inputs and outputs. So I'm going to go to the IO planner. And I'm going to map the IO to the IO on the FPGA board itself. Oh, this thing takes a while to open. All right, so we're in the IO planner. So this is basically what the chip package looks like of the FPGA. So we have the IO defined in the bottom here. This might be a bit small to see, but we want the input to be the pin that's connected to the reset button. So let's see. So I actually have the definition of the board open here. So each dev board, each FPGA board basically comes with like a little bit of a description, documentation about how the pins are actually mapped to the pins on the FPGA chip itself. So you can see how our clock pin is mapped, where the reset button is mapped. So we can see the reset button sits on pin 101. So I'm going to go ahead and map that. So we have our input, which is this guy right here, and we want this to be connected to P101. Perfect. And for the LEDs, we're just going to map them to P68, 78, 83, and 89. So these are the 4 LED pins on the board. So if we go here, P68, P78, P83, and P89, was it? Yeah. I'm just going to go ahead and save that and close the pin planner because we're basically ready to go now. Then I'm going to hit configure target device. So you can see here that we have an error in place and route. So if I view the report, we can see it's warning us about clock IOBs have been found that are not placed in optimal clock IOB clock side pair. Interesting. Oh, okay. We don't care about that. That's probably because we're, yeah, it's probably because it figured out that we're clocking a counter from a reset IO pin instead of the actual clock signal. So the nice thing about these FPGA boards is in order to prevent timing errors on them, they actually have dedicated routes for the clock signals to go so that the clock signals can reach anywhere inside of the FPGA very quickly. Instead of having to travel through lookup tables and pass-throughs, it basically just, the clock signals basically just directly hooked up to basically everything that's clockable. And in this case, we're actually hooking up the reset IO pin to the count, to like the clock signal of the counter, which we want to increment. That's why it's warning us. And this might actually cause timing errors. But in our situation, we don't really need to worry about this because we actually intend for the reset signal to be the clock of the counter. And we don't have anything else that depends on that kind of timing. So for us, it's not really going to make a difference. So we can just kind of ignore it. So we just need to add this line right here that it's suggesting we add if it's okay in our design, which it is. So I'm just going to go ahead and refresh this. How do we refresh? There we go. So I'm going to go to the UCF file, which defines the IOs that we've mapped. And then let me just correct this. So we're just going to set clock dedicated route equals to false to ignore this error, or it's going to demote it to a warning. So it's still going to show up as a warning, but it's not going to cause any builds to failure. So let's go ahead and retry this. So I'm going to regenerate the programming file, see if that works. And then we're going to run it on the FPGA. All right, so with that done, I'm going to configure the target device now. So I'm just going to initialize the chain. All right, so let me add the configuration file. So it's this main.bit right there. Okay, so this, no, I don't care about that. Bypass, okay, whatever. All right, so here you can see 2 devices that are connected to the JTAG. Now the first device right here is the actual FPGA itself. And the second device is the ROM chip that's on the FPGA board. So if I can show you here, where's Chrome? So you can see here we have this XCF4S chip right there. So that's a ROM chip that basically stores the configuration onto the FPGA board, because everything on the FPGA chip itself is volatile. So every time the FPGA loses power, it also loses its configuration. So everything you've programmed onto the FPGA will disappear once it's powered down. So that's why they have this ROM chip right here, which you can store your programs onto, and then every time the FPGA is powered up, it will load its configuration from the ROM. So that you don't lose, so you don't have to reprogram your FPGA with a JTAG every time. So that's quite nice. So for now, let's just program the chip itself. So I didn't program the ROM, I just programmed the chip directly. So if the chip now loses power, it will lose its configuration. So let me demonstrate that. So here you'll see the chip is currently programmed. So we've got one LED on, and every time we press this reset button, we want it to increment the counter, right? And there we can see it move to the next LED. Second one, it's not working as nicely. And the reason why it's not, oh, there you can see it did some weird stuff right there. It jumped a few LEDs. The reason why that happens is because of a bouncing problem on the reset button. So, but before I talk about that, let's first see what happens when we power this down and back up again. So there you can see I just resetted the power. And now it's running the demo program that came with the chip. It's like it lost the configuration that we just programmed onto it. So let me go ahead and reprogram it. So I'm going to hit program. There we go. So here's our Logisim circuit running on it. But it doesn't work as intended, as you can see. It behaves a little erratically. And the reason why that happens is because of bouncing on the reset button. And this is not a problem on FPGAs really, this is a problem in anything electronic really. When you have an input button or a switch or anything that needs to make contact, you basically always have this bouncing problem. So let me show you what this bouncing problem actually is. So I'm just going to open up Paint here just to demonstrate this. Let's see. Paint. So in the simulator, what we have is in Logisim, for example, once we initially the push button, right? The state, let's say we have our high state and our low state. Now, initially the push button state will be low, right? And then when you press the button, you would expect the state to go high and then stay high for as long as you press it. And then once you release the button, it should go low again and then stay low. That's how it works in a simulator. That's not really what actually happens. In real life, it's actually a little bit more messy than this. So this is how you would expect it to behave, but how it actually behaves is more something like this. So you once again have, let's see, our high state and our low state. Initially, the button starts off with a low state, but when we press it, you see the thing is, I don't know if you've ever noticed, if you have like a light switch that's not properly switched over or something, and it's a little bit intermittent, then you'll get like a flickery light or something. It's basically a similar thing that's happening here. So we're getting multiple triggers because as soon as this button starts making contact, it will jump high, but it will jump low again, and then high, and then low again. And this might help a few times. And then eventually it will reach a stable high state, right? And then same thing when you release the button, it'll go low, it might go high again, low, high, low, and then finally it will stabilize at the low state again. Now the problem is these jumps on the rising edge and falling edge. These jumps will cause multiple triggers to be detected on the chip. Now with FPGAs, this is more problem than with microcontrollers, because with microcontrollers, you have like your processing delay. With FPGAs, everything is in real time. It's basically real-time actual logic. So this, and because this happens really quickly, it's only really a problem when you have real-time logic. So if you have an Arduino or something, you might not notice this problem as much. You might still notice it. It will probably still be a problem, but it won't be as bad of a problem as it would be with discrete logic or with FPGAs, for example. So in order to solve this problem, we need to implement debouncing on the FPGA. Now, I think that's actually a topic for another day, so I'll just show you what the behavior looks like with debouncing implemented on the chip itself, but I'm not actually going to show you how it works. I think I'll make a follow-up video on that. All right. All right, so here I have actually added some debouncing logic. So it's just a small little debouncing circuit. In the next video, I'll describe this in more detail and the approach to debouncing in more detail. But for now, I just want to show you what it how nicely it runs with debouncing actually implemented. So as you can see here, every time I now press the reset button, the next LED actually flashes like that. So you can see it works really nicely now. So yeah, that's that. Now the final thing that I could show is programming the EPROM on this thing. So currently we have the situation that every time the device loses power, it will also lose its configuration, but we don't want that. We want to keep the configuration when it loses power, and that's what this ROM chip is for. So in order to program this, we need to first create a PROM file. So I'm just going to add my device here, and I'm going to select the right chip. I'm going to just add to storage device and add it right there, and then I'm just going to hit OK to revision 0. Then I'm going to select the programming file, just this main.bit. I don't want to add another device, so I'm just going to hit generate file. So I'm not sure where that generated, untitled.mcs. Untitled.mcs. Okay, so now we can go ahead and program this. I put it in here for some reason, untitled.mcs. So now we can go ahead and hit program. I'm just gonna hit yeah, apply and okay. So now it's programming. This kind of takes a while because these ROM chips are really slow. So, but I'll show you how it works after it's programmed. All right, so the debouncing has been programmed to the ROM. So now I'll just show how that works. So you'll see that if I remove power and I reapply power, you'll see that the device kept its configuration. So every time I press this button, our LED program will work. And this will happen every time it loses power. So it will just load up our program again every time. There we go. Oh, and I've also noticed the reset button also seems to be active high instead of, or active low instead of active high. Because you'll see when I remove power and apply power initially, it actually jumps to the second LED. So that's an indication to me that the reset button is active low. So we probably should have put a NOT gate onto the reset button as well, but we didn't, but it's fine. Still works just fine. Yeah, another indication is you'll see that if I press the reset button, nothing happens, but once I release it, it switches. So yeah, that also means the reset button is definitely active low. So yeah, that's that, and I think I'm gonna leave it there for this video. I don't want this video to be too long, so in next time I'll probably look at the debouncing stuff. Cool, stay tuned and I'll see you then.